Good afternoon, everyone, and welcome to my talk. My name's Paul Rice. I'm head of electronics at Leonardo. A bit about my background. I'm background in RF and microwave technology, having done a PhD with QinetiQ and Malvern. I've predominantly worked in startups, UK, Europe, sometime in Canada. And for the last few years, I've been working with Leonardo. So today I'm going to talk about miniaturization and power efficiency and the continuous drive to smaller, more efficient hardware, and how it can enable some of our next generation sensors used in the electronic warfare domain. There's my email. If anyone wants to contact me, I'd be happy to engage and follow up. So just briefly, one or two slides on the company. For those that don't know Leonardo, Leonardo's a global aerospace and defense company headquartered in Italy. We're around about 50,000 people globally. Main workforce, Italy, UK, subsidiary in the US. We sell our products into 150 plus countries, and you'll see why with the range of products we offer. We're integrated into a vast global supply chain. We realize the capabilities that we develop across several divisions, including helicopters, aircraft aerostructures, electronics, cybersecurity, and space. In the UK, we're around about 8,000 people split out across 8 sites. Edinburgh focuses on radar, Luton, Lincoln, predominantly electronic warfare, defensive aid suites. Southampton and Basildon, comms and optoelectronics. We have a large helicopter workforce in Yeovil, cybersecurity in Bristol. Newcastle is a relatively new office that we've established with a focus on digital engineering, artificial intelligence, next generation sensors. Just to start a bit of context on what we're doing, a very high-level timeline here of a range of products across the domains of sensing, engaging, and protecting platforms. Going way back, you can see the names of numerous companies that the workforce and facilities have been owned by over the years. Most recently, 2017, we became part of Leonardo. So that's the past. The future, we're involved in the global combat program. So a trinational program between the UK, Italy, and Japan to develop the next generation platform. And Leonardo is heavily involved in developing the sensors for this platform across the range of radar and countermeasures. So why? What technology do we need to enable the development of those platforms? I've chosen this example to show how technology scaled over the years, with a view on computing. And when you look at the defense space and the products that we're developing, they're a high mix, lots of different technologies, but a relatively low volume. And so there are some instances where the defense industry is developing new technology for specific capabilities that are absolutely must-have. But we also have to leverage technologies that have been developed at scale in consumer markets. And so I think this trend's interesting here, showing the progress that we've made from initial mainframe computers through to laptops, through to this smartphone device, which has so much more capability, is really power efficient, and is portable. And it's those capabilities that we're looking to take into some of our next generation products that I'll talk about soon. Now, I couldn't talk about scaling without some reference to the exponential growth in transistor count, and a reference to Moore's law. What this is showing is the transistor density in package, and there are so many more innovations along this timeline, but I picked out a few key ones. Going through above the line, we're looking at the transistor technology through to smaller and smaller nodes for higher speed processing and capability. But that isn't any good on its own, and it has to be accompanied by packaging as well. And you can see the evolution in packaging through to from dual inline packages through to surface mount with no legs, system in package, and more recently 2.5 in 3D packaging. And this is all driving to in the silicon world. This is driving to 100 million plus devices per square millimeter. But is it reaching its limit? Looking at where Intel think they are and where they can go, they can see this stretching out through adopting different transistor formations, developing packaging, and there's some other interesting innovations that I think will support capability development, including chiplets, picking out the specific device functionality that you want and integrating those in a package, integration with compound semiconductors and silicon for different functionalities. And then of course you've got the road towards quantum and photonics. What I haven't specifically called out in this diagram are some of the RF and microwave technologies, which are key to some of the sensors that we develop. And they have very different geometries to, I'm not going to get a pointer there. They have very different geometries to silicon, and they're typically around the 250 nanometer to 100 nanometer size node. And there, the trade-off is all about frequency capability, but also power handling. So we have all these technologies, and they're incredibly important for us to develop a whole range of different systems and be successful in the modern operating theater. So today, and moving forward, the theater we'll be operating in is multi-domain. We're looking at space, land, sea, whole range of sensors interconnected across that domain. Now that's challenging enough when you're the only one that's operating there, but when you're also having to operate in a congested and contested EM spectrum, it's ever more important to have these technologies to allow us to sense, disrupt, and get the communications between platform to platform that is absolutely essential. So increasing levels of system capability, sophistication, smaller size, and improved efficiency. I just want to pull out one example here, a very high level, but just to give you a feel of what's possible. So I'm showing a very high level subsystem diagram here. Typically involving an antenna, a transmit receive module, some level of frequency conversion, power supply processing, and thermal management. I've pulled out the transmit receive element. So this is all about being able to transmit the power level sufficient to disrupt an adversary's tracking system. And so it's about the power and efficiency that you can achieve within a certain size of semiconductor space or package size. And there's been many advancements, like I'd mentioned, in terms of packaging, and we leverage those. But a key enabler here are the use of different semiconductor materials. And so just to give you a visual example, on the left-hand side there, you have a power lineup for a high power amplifier based on a gallium arsenide technology. Typically achieves around a watt per millimeter, and if you stack 8 of these devices together, you could achieve about 5 watts. Contrast that with what you could achieve with a gallium nitride based technology. It shows you how you can reduce that scale, achieve more power. So you're effectively achieving double the power with half the size of the chip. Smaller device size, enabling a broader frequency performance, and a simpler power supply configuration, because you can power the gallium nitride device from a higher voltage bus. And this is the kind of development and evolution we're looking to leverage in some of our next generation products. I've got a few examples of those here. So this is our Bright Cloud product. This information's on our website, and if you want to find out some more about it, there's some contact details on there. So this is the world's first digital RF memory expendable active decoy, and it's made possible by those innovations I described on the previous page. So this device is a self-contained jammer, and it's designed to be used when there's an incoming missile on the target, and it's ejected from the plane to present effectively a ghost of the platform that you're trying to develop. So it's receiving RF energy from the incoming missile. It's processing that energy and transmitting it back, and confusing the missile as to where the real target is. So this is very much a last resort for the pilot in the platform. Hopefully he or she doesn't get in that situation. But to give you an idea of the scale of this product, it's about the size of this bottle of water here, and within that volume there's a like propulsion mechanism, there's an antenna, there's the RF components, transmit receive module, all the processing behind it, to allow this device to work. Another example of what's being enabled through miniaturization of technology. We've recently launched our Brightstorm range of products. Now they're similar in some ways to Bright Cloud, except they're designed to be used before an adversary has launched an attack. So these are low swap stand-in jammers. Now, before these, you typically conduct this operation from further away. You're effectively a standoff jammer, at a greater distance, needing a much larger system, needing much higher power levels, probably on a crewed platform. So, much greater loss if anything were to happen to that platform. But with being able to reduce the size of the electronics here, we can now develop these low swap stand-in jammers, which are designed to fly on uncrewed systems, and they are attritable. So the whole point of this system here is to fly on these uncrewed systems and confuse enemy defense. And you can see in the diagram on the top there, the system's flying at the rear, but it's presenting multiple potential objects that an adversary radar would pick up and be confused by. So just to summarize, we've talked briefly about technology scaling, some of the future challenges and opportunities, how reduced swap, component size and efficiency is really enabling a whole raft of new sensors and products in the defense space, and I provided a few examples. Happy to take any questions. Like I said at the start, if anyone wants to reach out, I'm here and follow up afterward. Thank you very much. No questions.
So, eventually it happens. They swap. So like low size, weight and power seems quite obvious why it'd be needed in a product like Bright Cloud for expendable decoy what's the sort of benefit for like a future generation aircraft on low swap?
Yeah, that's a good question. So, yeah, there's not only benefits on these smaller, more portable and mobile systems, but if you look at the systems and components on a future platform, particularly the radar part, which could contain hundreds of elements. So making each of those elements a bit smaller, reducing losses, improving efficiency by a few percent, you can have a massive impact at the thermal load of that system, making dealing with the heat a lot easier.
Thank you.
Thanks.
Okay, if there's no questions, we could conclude there. Oh, there is one.
In the situation where you've ejected your small device to confuse a chasing aircraft or missile, how we guess we're fleeing from this threat, so we're supersonic. Surely the radar or whatever is tracking you can differentiate between your aircraft, which is supersonic, and a device which has been ejected and it's not, I'm assuming it's not powered enough to maintain supersonic speeds itself. So, it would be, I believe it would be relatively easily for a radar to choose you as the target still. I mean, has this device been, is it in service? Has it been tested?
Yeah, absolutely. It's been tested fully, and I mean that's the whole point of the device, that it can create an image, if you like, by receiving the kind of missile targeting RF energy, receiving it, processing it, and transmitting it back at sufficient amplitude to effectively present an alternative representation of the aircraft. So this is like a real device, has been tested, and is being deployed. Okay, well, I'll say again, thank you very much. Hope you enjoy the rest of the show.
Good.